Okay, so classification trees, we do it for categorical data, and then I don't know why I bothered writing all of these formulas, but basically we have a few different measures for evaluating the performance of a classification tree. And so one is the Gini index. The Gini index is it's like this is the Gini impurity index, and this was kind of based on economics, and it used to be like for inequality of income, and you can either have a society where everybody makes all the money, and that has the lowest Gini index, where it makes everybody has the same amount of wealth, and then a different society where one person holds all the wealth and everybody else has no wealth, and that's maximum inequality, and that's the highest Gini index. And so, but this is, I guess, for the impurity, and it's just kind of p hat times 1 minus p hat. So this is maximized when, if you're talking about like proportion, it's 0.5 maximizes it, versus if you ever reach a proportion of like 0.99 or 0.01 or or like 0, okay, complete purity, this goes down to 0, right? And so this comes out to this, and so you can use the Gini index, because now you don't have the R squared values, right, or RSS, to make the decisions. And then there's another thing called entropy, and there's debates about like which ones should we use? Should we use entropy versus Gini? Turns out that they're like the same. It doesn't really make a difference. Okay. And then so as far as classification, I don't know if I want to talk through all of this. Okay, you can look through it, but basically the same idea. You consider every single possible split, and then you decide which splits are good or bad, right? Good splits versus bad splits on the thing, and so I think the split you make between 3 and 4, and you'll get you classify everything less than 3.5 as A, and classify everything greater than 3.5 as B, and you'll get the misclassification. There's only one error there, and you get a low Gini index there. Okay. Okay, and then and you can do the same kind of thing using R, and it says you should split at 3.5 as well. Okay, the other concepts here, and I didn't write enough here, is the idea of bagging and random forest. Okay, and so these are ways to improve the performance of a decision tree. Okay, so what bagging does is we are doing bootstrap for a decision tree. Okay, and so you don't have to follow any of this code, but basically the decision tree, we had these observations, and we made the decision tree based on our data. And what bagging does is it says, well, what if we bootstrapped our data? And so we get different samples, okay, and we fit a decision tree to a slightly different sample, and we build the decision tree on this kind of the slightly different sample that I have. Okay, so chances are those two decision trees will be very similar, but they also might be slightly different, right? So here, if I run a bootstrap sample on the original data, we said the split should be done at 3.5, but based on this random sample of data, the split I get, just because of randomness, says I should make this split at 2.5. Okay. And then if somebody else did a bootstrap sample, okay, here when you do the tree, it says no, my results end up, you know what, I think okay, I think I'm having the issue of the random sample performing differently. Okay, so the text in your handout doesn't match the results in this, and I didn't catch that when I printed it. Okay, so it says that the sample selected row 5 twice, but it didn't. It selected a different thing. Okay, all right, that's troublesome. Okay. So something happened with my my random sampling. But basically the idea is every time I do a bootstrap sample, I'm going to get something slightly different, and then the resulting tree ends up a little bit different as well. Okay? And so if I so what's going to happen is that now I have a bag of 3 different trees. Okay? And so this is technically wrong, or technically doesn't match the results that I got. But if we have a test case with x equals 4, when you feed it through the first tree, it says we should predict this value, 7.667. Okay, that doesn't match the results of the thing, but just imagine a tree where, based on the bootstrapped data, it says x equals 4, we predict 7.667. And then the second tree where x is 4, it says we should predict 7.5. And then the third tree says when x is 4, we predict 7. Okay, so we have 3 slightly different trees because they're based on slightly different random samples of data. And so, so the bagged prediction is going to be 7.3889. Okay, this is not the result of any one tree, but it's the average of 3 different trees that are based on 3 bootstrapped samples of data. Okay, and so what this does is it basically just introduces extra kind of variation, and it forces to give you answers that are slightly different, but then by averaging them, you're hoping your predictions are a little bit more stable, I guess. Okay, by getting things that are kind of having more and then taking the average is a little bit more stable. Okay, so that's what bagging does. Okay, and you can perform bagging in R, and then there's random forest. Okay, and so random forest is like bagging, except you further cripple the prediction of the tree. Okay, and so the way a random forest works is you say, you know what, when I did bagging, every single one of my trees, assuming you have high dimensional data, right, and so let's say you're predicting the price of a house, okay, based on features of the house. If you did bagging, so despite taking random samples of your data, bootstrapped samples of your data, when you do bagging, you might find that every single tree says, the first split should be based on house square footage, okay? And because of the bagging, maybe it's we'll split it at square footage over 1100 versus split it at square footage at 1150 versus split the square footage at 1,000 square feet, or split the square footage at 1,200 square feet. But it might be that every single tree says the first split should use the variable square footage, and the bagging process makes that split just ever so slightly different with different values. Okay, but random forest says, I don't want every single one of my trees to be dependent on this one variable. Okay. So what random forest does is says, you know what, I want you to build a tree, but you know what, you are not allowed to use square footage as a predictor. You have to use a different variable, okay? And so what that does is it forces the tree to build something else, right? And so it's kind of like, I want you to do the best, but don't depend on this thing, okay? Do the best you can, but you're not allowed to use these predictors, which are maybe too powerful or something. So you end up getting another tree that is probably on its own not as good, okay? Because we've taken away like an important predictor. We took a predictor like square footage away, and maybe that's a very important predictor. So this tree all by itself is not very good. But when you have a whole bunch of these trees, say a forest, okay, and you take the average of all of them, it turns out by having these trees that by themselves don't perform well, but when you average them out, it turns out that prediction ends up doing a lot better, okay? From a kind of by having this kind of diverse set of trees, each of which are less than optimal, but by having a whole bunch of these different trees working together, the random forest actually ends up performing quite well. Right? And so random forest is quite popular. Random forest does take a long time to run, okay? A lot of times, okay? Because it has to build a whole bunch of different trees, and each tree takes a while to create, and each tree that it creates also produces different, uses different predictors, okay? So we bootstrap the data, and then we fit a tree, and when we fit the tree, we say you're only allowed to use these predictors. You're not allowed to use all of them, okay? And then you're going to fit a whole bunch of these trees, and each one's going to be different, very different from the others, because they're all using different predictors, and then you average all of those predictors. So that's random forest, okay? And I think that's where my notes stopped, okay? And then the last section, or the last kind of idea, is boosting. And again, all of these methods really only became possible because our computers have gotten so good. Okay. So boosting is the last topic. And what boosting does, and so when you do random forest, you can create this, that's from something else. But you get the variable importance graph, which tells you which variables turned out to be the most important. And because it can figure that out now that it says, we've purposely made good and bad, not good and bad trees, but just trees without certain variables, okay? Okay, so the last topic is boosting, okay? And so boosting is, technically, this can be applied for any kind of statistical learning method, okay? And the idea here is that when we fit a tree, we fit it to the residuals of kind of the previous shrunken tree, okay? And so what is a shrunken tree? Well, we start off and we say, you know what, when you make a prediction, you are not allowed to actually change the last result. All you're allowed to do is give it basically a plus or minus vote, okay? Like you get to just steer the rudder just a tiny bit, okay? And so, you create a tree and you say so maybe, let me go back to my, okay, so if we, in our very first example, we said if we didn't have a tree, we'd just predict 4 for everybody, okay? And then when we make the split, we said, okay, you know what, for everybody less than 3.5, we are going to predict 1.67, and over here we're going to predict 7.5, okay? And what boosting does is it says, sure, go ahead and make the split at 3.5, but you are not allowed to drastically change your prediction from 4 to 7.5 or from 4 to 1.67, okay? Instead, you can only make an incremental change. And so what's going to happen is that when you do boosting, after the first iteration, okay, so the original prediction was right here. After you do the boosting, it goes up. These are the new predictions, okay? You basically have, this is kind of like lambda times like the difference from the tree, okay? And so so this is what we end up getting, okay, after the first iteration of boosting, okay? And then we do boosting again, and probably we fit another tree, okay? And probably it's going to say like, okay, I want to go back up to here, okay? And then so then maybe after the second iteration, it's going to just kind of increase this. But what could end up happening is it just pushes these things down, and so it basically says you're not allowed to drastically change your prediction very much at any time. You're only allowed to just incrementally change your prediction based on these things, and so the result is you end up getting this kind of this finely tuned model after many iterations. It's so I'm sorry. The boosting approach is what we call a slow learning method, okay? So the original decision tree where we said split it at 3.5, they call it is fitting the data hard, okay? Okay, so unlike fitting a single large decision tree to the data, which amounts to fitting the data hard and potentially overfitting, the boosting approach instead learns slowly, okay? So given the current model, we fit a decision tree to the residuals from the model, okay? And we just kind of incrementally do these things. And so what you see in this thing is that the boosted model is a lambda, and the lambda is like this small, like 0.1 kind of shrunken version of the tree. And it just says you're not allowed to just jump from, the model where you just predict 4 for everybody to 7.5, but, instead of adding 3.5, you will add 0.35 or something, okay? And so it forces this thing to learn slowly, and it turns out that the resulting performance of a boosted kind of tree ends up doing quite well, okay? There's not a whole lot of explanation in our textbook about it, other than this algorithm, which isn't very detailed, okay? However, and I guess we'll see how much time we have in the course. Boosting especially with kind of the advent of XGBoost, which is kind of this a version of boosting which they call extreme gradient boosting, but at the heart of it, it's still a boosting idea. It has performed very, very, very well in all sorts of prediction problems, and so maybe we won't get into the details or the math behind boosting, but we can kind of see kind of the performance increases and outputs of that. Okay, I'm behind. I have to write up your homework assignments and create your regression model problem. Yes, question? Yeah, that's also my bad. Eventually, we'll take care of everything. It's all on me. It's all my fault for everything being delayed and stuff. But we'll get everything up and running, and we'll see you guys there. The TA told me she's canceling or postponing today's session. So okay, I don't know when it's rescheduled to, but for the attend that for the lab on the tree stuff. I have to fix the notes because I think the random sampling didn't match up with what actually happened. Okay, we'll see you guys on Wednesday.